So guys, in the previous classes we have seen the concept of combinational circuit, right? So combinational circuit means which is going to produce the output simply based on the present input, which is not going to depend on any kind of memory or any kind of previous history. That is what we call it as combinational circuit. Whereas if you take the sequential circuit, which is going to produce the present output based on the present input along with previous history, right? Yes. Right. So for the combinational circuits, we have seen various kind of examples. Among those, one kind of example is arithmetic circuits, where we have seen the adders, half adder, which is meant for the purpose of adding 2 bits, full adder, which is meant for the purpose of adding 3 bits, binary adder, which is meant for the purpose of adding n number of bits, and there is a drawback in the binary adder. That is the reason we are moving for carry look ahead adder. So the reason why we are moving for carry look ahead adder is because of propagation delay, right? So in binary adder we are going to have more propagation delay. So to overcome this drawback, we are going to construct special hardware for the carry look ahead adder. So that's the reason propagation delay will be very less in carry look ahead adder. Okay, fine. And then we have seen subtractor. Among those, half subtractor is there, which is meant for purpose of to subtract one bit from the other bit. Full subtractor, which is meant for to subtract from the 3 bits. Binary subtractor, which is meant for to perform n bit subtractor, right? So if you are able to observe binary subtractor, can we able to do, like, if I would like to perform subtraction from A with B, I can able to write this as A plus of minus B, right? So I can write B as 2's complement of B, right? Then indirectly I can say that here also I am going to performing addition. So indirectly I can able to use here also a binary adder, right? That's the reason we discussed one more kind of a circuit where the circuit will be acted as both adder as well as subtractor, right? And then we have seen multipliers, where which is meant for the purpose of multiplication of 2 single bits or 2 bits, or it can be a kind of n bit multiplier also, right? So we have seen the basic procedure how to perform the multiplication of 2 n bits, right? So there is a drawback here. To overcome that, we are moving for register shift method, where we can able to reduce the number of additions, right? And coming to this one, we are going to overcome with the help of Booth's algorithm. Here also we have seen various kind of procedure how to perform the 2 n bits multiplication, like along with some kind of flow chart, and also we have explained with an example, right? So this Booth's algorithm advantage is it can able to work for both signed numbers as well as unsigned numbers. That is the advantage of Booth's algorithm, right? So I think we have seen examples also. Next kind of example of combinational circuits is conversions. We can able to convert from BCD to XS3 as well as XS3 to BCD. This also we have seen, right? So basically, when you would like to ask to construct any kind of a circuit, what you have to do, first you have to identify the requirements, or I can say that you have to identify various kind of specifications. Once you identify the specifications, then you can able to simply construct the truth table for it. Then we can able to derive the Boolean equation, or I can call it as Boolean expression. After that, we can able to construct the circuit. Then if you want, you can basically verify it, whether it is going to be perfectly working or not, whether our construction is perfectly or not, whether the realization is perfect or not, right? This is the basic procedure what we are going to do when you are going to construct any kind of digital logic circuit, right? Based on this procedure, we have implemented BCD to XS3 code as well as XS3 to BCD code. And also we have seen one more example, which is a kind of comparators, right? Which is meant for the purpose of comparing 2 1 bits, or comparing 2 2 bits, or comparing 3 bits, or 2 3 bits, or comparing 2 4 bits, like that. We can able to construct a circuit for comparing 2 n bit numbers, right? This is what we have seen, right? So for the coming class, what you can do now? So you can able to implement the different kind of comparators are there, like converters are there. Like for example, if I am going to give a binary number as input, can we able to convert it into gray code, right? We have seen the earlier the procedure also, how to make how to get BCD to gray code, right? So you can do that for the coming class, and also you can do it for the opposite, gray code to binary code, right? So basically guys, if I am going to have binary number 1000, its respect to gray code is completely different. Am I right? So gray code properties are completely different. Gray code properties are something like, it's a kind of reflexive property, it's a Unicode, right? It's a kind of cycle code, right? These are the things we have seen, right? So first what you have to do when you are trying to solve this question, if you are able to understand the conversion of BCD to XS3 or XS3 to BCD, you can able to understand, right? So first you have to identify what are the requirements are there here. What are the requirements are there? Requirements means something like, what do you mean by a binary number? And then what are the valid binary numbers? What do you mean by gray code, and what are the valid gray codes? That is what the requirement. Then you have to simply construct the truth table. So in truth table, what we are going to do? We are going to get binary number as input. Based on this input, what we need to produce the output? You need to produce the output as gray code. So here we will get the gray code. For that you are going to select the lines, and you can able to construct the equation. Then you can able to construct its respect to circuit diagram. The basic procedure, right? Similarly, gray to binary also. You have to understood the first what is the meaning of gray code. You have to understood what is the meaning of binary code. Then you have to basically construct the truth table. Truth table input is what? Input is gray code now. Output is binary code, right? So based on the output, we are going to construct the equation. Then we can able to construct its circuit, right? Simple. Like if I take BCD to XS3, if I am going to have a number like 4 zeros, is it a valid input or not in BCD? Yes, it is valid input. In XS3, what is the respective output? It is 0 0 1 1. Very good. So like this, you are going to construct all the valid things. It's respect to all valid outputs. If I am going to say that 1011, is it a valid BCD number? No, it is invalid. So at that time, what is the output you are going to expect? You are not going to get any output. That's why I am going to say that it can be a don't care, right? So based on that, if I am going to have 4 bits, what is the range of these 4 bits? Total 16 numbers are possible. Those 16 numbers are from 0 to F, right? Among those, the invalid numbers are from 10 to 15. So for 10 to 15, you are going to get don't cares. So like this, you have to do. Right? Similarly, you can able to do another one. If I am going to give a BCD number, you have to construct a 7-segment display number. 7-segment display number. See, like what is the meaning of this one means? You can able to observe this kind of numbers somewhere. I have observed this kind of symbols, this kind of number. What is the meaning of this one? This one I can call it as 7-segment display. Right? Why it will be called as 7-segment display means that I will let you know. So is it done in the lab? No, right? Okay, fine. So what you can do now? First you have to understand what is the meaning of BCD. I hope you know the meaning of BCD. BCD means the ranges are from 0 to 9, and 7-segment display means it will be like this. If I am going to have the structure like this, can I able to give naming something like A, B, C, D, E, F, and G? How many characters are there? How many individual numbers are like alphabets are there here? 7, right? So as we are going to have 7 individual alphabets, I will call it as 7-segment display. 7-segment display, because it has having 7 unique alphabets. With the help of 7 unique alphabets, I can able to generate any kind of a number. For example, if I would like to generate A, what you can do, ma? See, let me take. If I would like to convert BCD2 as 7 segment display. BCD2 7 segment display. My structure will look like this, where it is having A, B, C, D, E, F, G. Sir, is this the order is only the I have to follow means? No, you can able to follow in any order, there is no problem. Fine. Now, if I would like to get the value 0, how can I get the value 0? By simply including A, B, C, D, E, F. Is it look like a 0? Yes, it look like a 0. Similarly, if I would like to construct 1, can I use F and E? Can I use F and E? Yes or no? Or I can able to use B or C. So this one I can call it as 1. Similarly, if I would like to construct the number 2, can I use A, B, G, E, D? So this is what I can call it as number 2. Similarly, you can able to construct all the numbers. If you would like to construct the number 9, what you can do? A, B, F, G, C. Right. So if you require like 9 like this structure, so if you like it to look like a kind of G structure, you can able to take D also. If you don't want the respective structure, you can take like only up to A, B, G, F, C. Right. So if you want, you can take this also. There is no problem. It look like a 9. So meaning that with the help of this structure, I can able to get all the remaining numbers. So this is what I can call it as 7 segmentation code. Right. So now, what are the inputs are possible for here? The inputs are BCD numbers. The inputs are BCD numbers. You can able to know that. For example, my inputs are 4 zeros. What is the output you are expecting? You are expecting a 7 segment display. You are expecting a 7 segment display. Now, what you can do now? So, in order to get 0 as output, BCD, if you are going to give the 0 number as input, you have to get the 0 as output, right? So, if you want to get the 0 as output, you have to activate A, B, C, D, E and F. C, D and F, right? So, meaning that what you have to make all these location values as 1, then I can able to get the corresponding number. Am I right or not? So, in this particular location, if I am going to make light bulb, it will look like a highlight. You can able to observe some kind of analog circuit somewhere. Right? So basically, right, if you go for any kind of olden days digital watches, you can able to observe this kind of things. Fine. So if I am going to give some names as A, B, C, D, E, F, G, right? So what need to be activated if you want to get 0? A should be activated, B, C, D, E and F, G should be 0. Right? This is the corresponding thing, right? As usual. Similarly, to get the value 1, what you have to do? You have to make either F and E as 1 or B and C as 1, right? So let us consider any one, right? If I take F and E as 1, I can do 0, 0, 0, 0, 1, 1, 0. Similarly, to get 0, 0, 1, 0, number 2, how we are going to get? A, B, D is 1, E is 1, G also 1, right? Remaining things all are going to be make as 0, right? So like this, you can able to take all the numbers from I think 1001 is the valid BCD number. So to get the number 9, what you are going to do? A, B, C, D, and then you have to consider G and F. E should be 0. Am I right? E should be 0, right? So like this, you can able to draw the truth table. What about the, right, if I am going to have 4 bits as input, the remaining numbers are like 10 to 15, right? Those 10 to 15 are going to be invalid. If I am going to give 1010 and so on, all 4 ones, these are going to be invalid. So I can make them as, don't guess. I can make them as don't guess. And once you construct the truth table, what is the final step you have to do? You have to derive the expression for each and every corresponding column. So to derive the expression 1 for A, what you have to do? You have to draw the K map. You have to draw the K map, and then so as here 16 bits are 16 values are there. What is the length of the K map? What is the length of the K map? Right, 16 bits are there, so it requires 4 variable K map, right? So you can able to give some names for it. Like for example, if I take as wxyz, you can make it as wxyz, and you can able to solve it. You are going to get certain expression. Right? So and similarly for B also you can able to do, for C and so on for up to G you can do, and you are going to get the various kind of equations, Boolean equations. From these Boolean equations, can you able to circuit diagram? You can able to draw circuit diagram. Finally, you can just verify whether your constructed circuit is correct or not. Right? So this is you can do for the coming class. Okay. So these three. One is conversion of binary to gray code, gray to binary, and BCD to 7 segment display. Okay. Fine. Okay. Now let's see. Like we have seen with comparators, and what are the other kind of examples are there that we have seen? One is multiplexers, and another one is demultiplexer. These are also another kind of examples for combinational circuits. And the another kind of example is encoders and decoders. These are also another kind of examples, right? Now in this class, we will try to view the what do you mean by multiplexer. Okay. Right. So here basically multiplexer means it's a kind of a combination circuit that we can understood, because it is an example of combination circuit. And the properties of multiplexer is which is going to take 2 power n lines as input, and it is going to produce 1 line as output. So this is the property of multiplexer. I mean, if you are going to have a circuit like this circuit is having 2 power n lines as input, where all these lines I can call it as 2 power n lines, which is going to produce 1 line as output. Right? What is the advantage of this multiplexer? You may have a question, right? So the advantage is you will get very less circuit size. Meaning that if you are going to take any kind of chips, right? Those chips are going to construct with the help of this kind of gate, like multiplexer, all those things, right? Instead of constructing with the help of basic gates, you are going to get very large size. So if you would like to reduce the size of the circuit, we can go for advanced version, where advanced version one of the type is multiplexer. Sir, can we able to implement the basic gate circuits with help of multiplexers? Yes, we can do. Right? That's the reason we are trying to learn one of the example of combinational circuit is multiplexer. Right? Basically, for example, if I am going to have two inputs, one input is 0, another input is 1, you are going to get 1 line as output, right? Basically, right? This one I can call it as 2 by 1 multiplexer. I will call it as 2 by 1 multiplexer, right? So meaning that here you are going to have 2 inputs and 1 output, right? Basically, if you are going to take one more kind of multiplexer, 4 by 1 multiplexer. What is the meaning of this one? It is going to have 2 square by 1 mux. I can call it as 2 square means what? 4 inputs are there. 1 line as output. Right? Now, if you would like to observe here, if I want to identify these lines inequally, how many bits are required? To identify these 4 lines inequally, how many bits are required? Can I take 2 bits? If I take 2 bits as A and B, A and B. The inputs are like 0 0, 0 1, 1 0, 1 1. Am I right? So can I able to give 4 names in equal or not? Yes. So this line simply defines as 0 0, 0 1, 1 0, 1 1. 1 1. Similarly, if you would like to identify these two lines inequally, how many bits are required? Only 1 bit. That's why I have taken only 0 or 1. Fine. Fine. Now, my question is here, if I am going to get 0 as input, like some certain inputs are there, how can we bypass this input to this particular location? Right? There are two cases are there. One is I can able to pass output as 0 or I can able to pass output as 1. How can we pass it? Right? There should be some kind of controller is required. Right? There should be some kind of control is required. That control I will call it as select line. I will call it as select line. How many select lines are required in order to control two particular elements? Only one, right? Because if I are going to give 0 as input, what is the meaning of 1? I am simply calling come 0, meaning that 0 will become and it will be hand over to output side. If I call as 1 come, then what it will do? Instead of 0, it will simply call 1. Simply call 1 and that will be as output. It will be as output, right? Similarly, if you would like to have a 4x1 multiplexer, how many select lines needed? How many select lines are needed? 2 select lines are needed, right? So meaning that, so to call them inequally, you have required some 2 select lines. One is like assume that S1 and S0. Technically, I will call it as select line 0, select line 1. And this one I will call it as I0, input 0, input 1, input 2 and input 3. Output I am going to represent technically as Z. Right? Basically, you can make it as Y also. But for the sake of your understanding, I am taking it as Z. Right? Now, if my inputs are 0 0, what is the output you are going to expect? I0. Right? I am simply calling please come 0 0. 0 0 is a name for I0. So that's why I am going to get I0 as output. Right? If I am going to pass 1 0 as input, what is the meaning of 1? Please come 1 0. What is the name given to 1 0? I2. So you are going to get the output as I2. Right? Like this it is going to be worked. Right? So if you are able to observe, the corresponding how this 2x1 mux is behaving. Right? So if you are going to name like this as S0, this as I0 and I1, what is the output? Z. Output is Z, right? So now can you able to construct the truth table for this? Yes. How can you construct the truth table? My name of the input select line is S0. When I am going to give the S0 as input, what is the respective output you are going to get? Right? So if you are going to give S0 as 0, what is the output you are expecting? I0. If I am going to give the input as 1, what is the output you are expecting? I1. So this one I can call it as characteristic table. I can call technical as characteristic table. Why I am going to call it as a characteristic table, which is going to define simply the characters of the multiplexer, meaning that what are for what inputs, how it is going to behave. If I am going to give the input as 0, it is behaving and it is going to produce I0 as output. If I am going to give 1 as input, it is going to produce I0 as I1 as output. Right? That's what I am going to say, that it's called as characteristic table. Right? From this one, if I am going to construct the equation, I can call it as characteristic equation. Right? So what is the output for Z? Z I can be written as S0 bar I0, S0 bar I0, or it may get as S1 I1. Am I right? If I am going to expect the output can be either S0 bar or I0 or S1 I1. Am I right? If I are going to give here S0 as input, here if I give 0, what is the output you are going to expect? I0. So 0 into I0. 0 means how I am going to represent S0 bar into I0. Right? So this is what I can call it as characteristic equation. From this characteristic equation, can we able to construct a circuit for it? Yes, right? So what you can do, you can simply take one AND gate. I think for So this is kind of sum of products expression, right? So you have two product terms, so you require two AND gates. One is taking the input as I0, another is taking the input as I1, and I think one is going to be complemented, another is going to be direct value for S0, and both are going to be combined and they are going to be produced as one kind of output. Am I right? So that output I am going to call it as J. Right? If you are able to cleanly observe the same circuit, I can relook like this, right? So try to observe. I am just making the indication. As S0. Finally, I am going to combine these two, and you will get like this, right? So I have written the same structure. Is it okay? Is there any problem? No, right? So now if you are able to observe, this is I0 and I1, S0, and I am getting the Z as output. If you are able to observe this circuit, is it look like a kind of a multiplexer or not? A kind of multiplexer? Yes, right? So where you are going to have two inputs, you are giving directly, and it is going to produce one output based on a select line. So internally, every multiplexer contains what? Again, basic gates only. Internally, every multiplexer contains basic gates. That logic they are going to be simplified, right? So means if you are going to have 2 by 1 mux, how many AND gates and how many OR gates and how many NOT gates are required here? According to this particular example, you require 2 AND gates, 1 NOT gate and 1 OR gate. So if you would like to implement any kind of this kind of requirement at any time, what you can do, instead of taking 2 AND gates, 1 OR gate and 1 NOT gate, you can simply take one multiplexer. That multiplexer is of size 2 by 1. Right? That is the advantage of multiplexer. Similarly, if you are able to construct the truth table for the 4 by 1 mux, assume that S1, S0 as input, or else I will try to take here only. Right? S1, S0 as input. Guys, try to make sure understood that the order in which you define the select lines, the same order you have to make the respective truth table. Otherwise, your results is going to be changed. S1, S0. What is the output you are going to expect? Z you are expecting. So when you are going to give 0, 0 as input, what you are going to get? I0, I1, I2 and I3. The same thing you can able to write it as Z as S1 bar, S0 bar into I0, S1 bar, S0 into I1, S1, S0 bar, I2, S1, S2, I3. This is what I can call it as characteristic equation. From this one, you can able to draw the corresponding circuit diagram. Which is of type 4 by 1 multiplex. Like this, right? So if I am trying to say that 8 by 1 mux, how many inputs are there? How many inputs I am asking? 8 inputs are there. 3, 6 and 8 inputs are there. How many select lines are required? 3 select lines are required, and you are going to produce 1 as output. Right? This is what I can call it as 8 by 1 mux. So which can range from I0 to I7, and I am going to make it as S2, S1, S0. You are going to get produce output as J. Right? Fine. See, I said already. So the advantage of this multiplexer is we can able to reduce its size. Right? But here the question is, can we able to implement any kind of Boolean equation or not? See, if I am going to have any kind of Boolean equation is in the form of sum of the products, then I can able to construct it with the help of AND OR gates. Am I right? Yes, I can able to construct AND OR gate, right? If I am going to construct AND OR gate, can we able to construct with the help of product of sums? Yes or no? You know the standard sum of the products, standard products of the sums. Once you know the idea of standard sum of the products, we can able to convert it into standard product of sums, so that you can able to connect with the help of OR AND gates also. So if you are going to have product of the sums, you can able to construct OR AND gate. Once you constructed AND OR gate, can we able to construct with help of NAND gates? Yes. If you are going to have product of the sums, can we able to construct with help of NOR gates? Yes or no? Yes. So the reason why we are moving from AND OR gates to NAND gates is to make them they don't know exactly how many kind of exact basic gates are required to implement, right? How many AND gates are required, how many OR gates are required, that they don't know exactly. That's the reason if you are able to try to implement with the help of same circuit, same basic gate like NAND, so that they don't want to bother about how many NAND gates are required. That's the reason we try to convert AND OR gates into NAND gates. Similarly, the same problem arises for OR AND gate also. That's the reason we come across with the help of solution called NOR gates. But here the thing is, if you are going to have a Boolean equation, can we able to implement with the help of 2 by 1 mux? Okay, fine. Or for example, if you would like to implement with the help of 8 by 1 mux, I can able to implement. But if I would like to implement with the help of 2 by 1 mux, is it possible? That's the question, right? Or else, whatever the equations that are possible in NAND or AND OR, can we be able to implement all the things in using the multiplexers? The answer is yes. Let's move. Why? Right? So, guys, for example, here, why I am saying that AND OR gates I can able to implement with the help of any other gates? The reason is this AND along with any kind of NOT gate is a kind of functionally complete. What is the meaning of functionally complete? I can able to derive any kind of Boolean expression. If I have the terms like OR and NOT, I can able to derive any kind of expression. Then I can call these two as functionally complete. Guys, in SQL or in relational algebra, you come across the terminology called set complete operations. Set complete operators. What are the various kind of set complete operators? Right? It will be a collection of some kind of operators. One is select, project, minus, join operation. Then operation, right? Meaning that with the help of those four, I can able to construct any other kind of like equation. That's the reason I am going to call it a set complete operation. Similarly, functionally complete means whatever the functions we are going to construct, those functions, if you are able to construct with the help of plus and not, I can able to construct with the help of any other kind of Boolean equation. Similarly, or if I am going to have and not, this also I can call it as functionally complete. Right? If I say that plus or and not, can I call this as functionally complete? Right? These two are independently functionally complete. If I am going to combine, I can call it as functionally complete. See, for example, I am going to have A and B with OR gate. This is what I require. And I am going to have only dot and not operators are there. Can I able to construct that? Try to observe. Can I make use of A bar dot B bar whole bar? De Morgan's law, right? Means, can I call now this and not are functionally complete for this OR operator or not? Right? Once you got OR operator, can we able to get again NOR gate? Yes or no? For this, what you can do? You can make some kind of complement. A plus B whole complement. This is what I can call the NOR gate. From this, can you able to get AND gate? Yes. So and so on. Means, once you have the inputs like and not, you can able to get all kind of other kind of operators, gates. That is what I can call as functional complete. Similarly, if you are going to take A plus B, or if you would like to get A and B, can we able to get A and B with the help of plus and not gates? Right? So these two are complement. I think it is correct. Right? According to De Morgan's law. So I can call this also functionally complete. Functionally complete, right? So means if I am going to have simply a plus and like or and not, or and not, or combination of all these, I can able to derive any kind of expression. That's why I'm going to call it as a functionally complete. That's why we can able to construct any kind of circuits there. Right? Now the question is, can we able to do like this or not? Right? If I am able to say yes, if I am able to say yes, I need to prove that I can able to get all kind of like NOT gate, AND gate, or gate, NAND gate, NOR gate, XOR gate, and XNOR gate. If I am able to get all these from one kind of like multiplier, can I say that it is functionally complete? It is functionally complete? Yes. So here, to make prove that, so I can say that multiplexer is a kind of functionally complete. That is the advantage. Multiplexer is functionally complete. That's the reason we can able to construct any kind of circuit. So that's the reason I am trying to do this example. So try to do. Let me have a 2x1 multiplexer. 2x1 multiplexer. If I say that it is 2x1 multiplexer, what are the inputs are there here? It should be S0, it should be Z, and it should be I0 and I1. I0, I1, right? Now, if I am going to give an input like X, I need to get the output as for NOT gate, X bar. How can we get, if I am going to give input as X, how can we get X bar? So that I can say that multiplexer will act as a NOT gate. So observe in the equation, what is the equation we are going to get, ma? Basically S0 bar I0 plus S0 into I1. S0 into I1, right? Try to substitute. This will be X bar into I0 plus X into I1. Right? From this equation, can we able to get the X bar? How can we get the X bar? If I am going to place I0 as 1, I1 as 0. I1 as 0. What is the expression you are going to get? X bar. So are you going to get the X bar or not? So now, what are the input should be for I0? Input is 1 and this input is 0. Can this circuit will act as a NOT gate? Yes or no? So this way you can able to make your multiplexer as NOT gate. Right? Similarly, for example, if I are going to have AND gate, how we are going to prove that AND gate is like, can we able to achieve it with help of multiplexer? Means AND gate requires how many inputs, how many select lines? 2 select lines are there. If I am going to have 2 select lines, how many inputs are there? 4 inputs. I need to have 4 by 1 mux. 4 by 1 mux, right? Now this should be I0, I1, I2 and I3. Now, in order to get the input, like for example, if I am going to pass an input like X and Y, what is the output I require? XY I need. XY I need, right? So now what you can do? Right? If you are able to construct the truth table for this, like S1, S0, it's look like this: 0, 0, 0, 1, 1, 0, 1, 1, 1, 1. 0, 0, 0, 1 means this are the inputs. These are the input, right? Means the inputs are like 0, 0, 0 and 1. If I am going to pass 3 zeros followed by 1, if I am going to here pass one value as 1, 0, what is the select line it is going to select? I2. I2 select chesindante, what you are going to get? 0. Is it correct or not? For 1, 0, output is 0. So that's why if you are going to pass 1, 0 as input, it is going to be selected this line and its line will be, it will be connected like this, right? Then you are going to get a 0 as output. So I can say that it is AND gate. Right? So here you may get question. Right? So can we able to implement the same thing with the help of 2 by 1 mults? Right? When you have seen the concept of variable entrant map, I have explained how to minimize the like K-map, right? So if you are able to observe here, observe if I try to combine these two. So if you are able to observe, like in 2 by 1 mux, in 2 by 1 mux, how many select lines are there? Only one select line is there, S0, and input lines are 2, I0 and I1, right? Now how can we convert the same properties to 4 by 1 mux to 2 by 1 mux? 2 by 1 mux, right? If you are able to observe here, now let me consider for timing, I will try to construct it for I1 so that it is easy for you. If I take it as S1, S1 for inputs S1 0 0, what are its respective outputs? What is respective outputs? 0, right? Means I can directly write it as 0. Write as 0. For the inputs 1 1, what is the output you are expecting? Which is same as S0. Which is same as S0. So can I write like here as S0? Now observe. So the inputs here are, when you are going to pass 0 as input, I0 should be selected, I0 value is 0. And for I1, the input is S0. The input is S0, right? Then you are going to get the respective output. This is the way you can able to reduce, right? So here the inputs are changed. Input is 0 here, input is S0. Here the input is S1, right? If you want, you can check, right? For example, if I am going to give the input like as 1 0, S1 is 1, S0 is 0. 1 will be here and 0 is here. 0 is here, right? If I am going to pass 1 0, as I am getting the 1 as input, what is the selected? It is going to be selected I1. What is the value of I1? 0. So this way it is going to be debugged. Okay. Similarly, if you are going to do with help of, so I can call this as NOT gate and AND gate. If you take OR gate, like you can able to do directly, right? 4 by 1 mux OR gate. So what are the inputs are possible for OR gate? 0, 1, 1, 1, and this will be like S1, S0, this will be J. This is 4 by 1 mux, because I can able to directly analyze. I can't do 3 able. Can we able to do it with help of 2 by 1 mux? Two by 1 mux. What you can do? Right, basically if you are able to observe in 2 by 1 mux also, if you are going to have, so what is the output you are expecting here in 2 by 1 mux for OR gate? For OR gate, the results will be like 0, 1, 1, 1, 0, 1, 1, 1, right? If I am going to have 0 as input, what is the output you are expecting? S0. If I am going to have 1 as input, what is the output you are expecting? 1, 1. So here, one input is S0, first one is input is S0, and second input is 1, when the input select line is S1. It is going to produce its corresponding J. Guys, is it always necessary to select S1 as the select line? No. Means here the same thing I can be rewritten as like this. If I am going to have 2 by 1 mux, this is I0, I1, and this can be S0 also. See, earlier I have taken this as S1. Now what I did, I have taken it as S1, S0. If I take it as S0, what you have to combine? This 0 and this 0 you have to combine. When 0 0 as input, what is the corresponding output you are expecting? 0 only. 0 only. Meaning that irrespective of the S1, you are getting again 0. Again 0. Right? What about the 1? If you are going to have the 1 1 as input, it is look like 0 1, the 0 1, same output. So it will be getting as S1. Right? So now I0 is 0, I1 is S1. Similarly, means these two are now equivalent. This one and this one, these two are equivalent. Is it okay? Yes. Now, can you able to define for this? What is the equivalent for this 2 by 1 mux OR gate? Can I write? This is S1, this is 1, this is S0. According to the previous and another kind of multiplexer. Is it okay? Yes. So similarly, can you able to draw the 4x1 mux for NAND gate? For NAND gate, what is the 4x1 mux? It's a simple, right? So if you are going to have 4 outputs, those 4 outputs you are going to simply connect it to here. So when you are going to get NAND gate, what are the outputs you are expecting? 1110, right? AND gate opposite is 1110. Okay, fine. Its expected output is J, right? This is 4x1 mux. Can I able to do with help of 2x1 mux? Yes, we can do. Yes, we can do. Right? For example, if I take it as S1, see, observe. I am making it as 00, 01, 10, 11, S1, S0. Z is what? So this should be 1110. We have selected the select line as S1. When 00 as input, what is the output you are expecting? 1. When you are having 1 as input, what is the output you are expecting? S0 or S0 bar? S0 bar. So S1 as input and my initial select line is 1, and what about another one? S0 bar. S0 bar. So can I able to implement the NAND gate also with help of multiplexer or not? Yes. Or I can able to do for the other also. 2x1 mux. If I S0 as input, I think you will get here as 1, here you will get as S1 bar. Okay, fine. This way you can able to do. Right. So for the coming class, what you can do now? You can able to construct for NOR, XOR as well as XNOR multiplexers in terms of 4x1 mux as well as in terms of 2x1 mux. Can you construct? Okay, fine. You can construct. Okay. Now means I can say that. So with these examples, I can say that a multiplexer is a functionally complete. Multiplexer is functionally complete. As I am saying that multiplexer is functionally complete, can I able to derive any kind of Boolean function? Yes, I can able to implement any kind of Boolean function. For example, I am going to have a Boolean function. Like sum of the terms. Basically, you can represent the another representation is canonical form, right? Sum of the products, right? So, for example, 0, 1, 0, 1, right? One kind of Boolean equation I can represent like this, 0, 1, right? So, or else if you take it as 0, 2, right? Can you able to draw the minterms for this? Can you able to draw? What are the minterms? For example, assume that S1 and S0 are the functions. S1 and S0 are the functions. So basically, how we can write them now? We can write as f of S1, S0 equal to sum of 0, 2. I hope you understood the clear meaning, right? So if you are able to draw the corresponding function before writing this one, actual function will look like this. S1 bar, S0 bar, or how we are going to represent the two? S1, S0 bar. That's it. This is the corresponding Boolean function. This Boolean function I have converted into this respective representation. Right? So this one can I able to represent in terms of 4x1 mux, the same output. Can I represent in the form of 4x1 mux? 4x1 mux, right? As I am going to have two variables, one is S1 and S0. These are the inputs. Now how many input lines are possible? 4 input lines are possible. These 4 input lines names are 00, 01, 10, 11, and you are going to get certain output as J. Right? Now try to observe these are the inputs I0, I1, I2 and I3. So what is the meaning of 0 comma 2? If I am going to pass either 0 or if I am going to pass 2, I need to get the output as 1. Is it right or not? See how you got this one, ma? This is the truth table only, right? 0 0 0 1 1 0 1 1 1 1 0 2. How I selected? For 0 I got 1, for the 0 1 I got 0, for 1 0 I got 1, for 1 1 I got 0. So if you are able to observe, this is S1, S0, it is Z. Right? Means, see, instead of taking all the procedure, I have taken directly this question actually. How can solve any kind of sum of the product expression, right? So here this expression you got because of all the minterms. How you got this one because S1 bar S0, this one because of S1 into S0 bar. The same thing I convert into canonical representation. From that I am trying to go for multiplexer. I am going to go for multiplexer, right? Now if I am going to give 1 0 as input, what is the output you are expecting, ma? 1, right? Means if I am going to give 1 0 as input, I need to get the output as 1. Means I have to select this line. Right? As you are giving 1 0 as input, automatically the properties it is going to be selected like this. But to make 1, what is the input required here? What is the input required? 1. The input required is 1. Similarly for I1 the input is 0. For I0 the input is 1. I3 input is 0. Now try to observe, if you are going to give some value like here as 1 1, what is the output you are going to expect? 0. Is it right or not? It will be connected, you are going to get a 0 only. Right? Now is it a kind of implementation using multiplexer or not? The same thing you can able to do with the help of AND OR gates also here. We can able to do with the help of multiplexer also. With the help of multiplexer, right? The same example you can be rewritten as like this. If I take it as 4 by 1 mux, I0 input is 0, I0 input is 1, right? I1 input is 0, I2 input is 1, I2 input is 1, I3 input is 0, right? So I can directly like this. For this input is 1, for this the input is 0 and my inputs are S1 and S0. Like this you can able to do. Okay, fine. Now question is, can we able to implement this with the help of 2 by 1 mux? Right? Once we construct anything in the form of 1 mux, you can able to construct with the help of lower mux also. You can able to construct with the help of lower mux, right? So what I can do now? So I need to minimize. If I would like to construct in the form of 2 by 1 mux, I am trying to say that S1 as input. Select line, and here the inputs are two inputs. One is 0, another one is 1, and I am going to get the output as 0. Right? To make it construct with the help of 2 by 1 mux, what you will do? Can I combine this 0 for the same 0 0 as input? What is the output you are going to get? 1 0. 1 0. 1 0 is dependent on what? S0. Meaning that, can I write like S0 complement? Similarly, if I am going to have 1 1 as input, I am going to get again 1 0, which is complement of S0 now. H0, right? So means here, what are the inputs for first line? S0 complement. What are the inputs for second line? S0 complement. Try to cross check. If I am going to give the input as 1 1, S1 is 1, S0 is 1. S1 is 1. When it is 1, what line it is going to be connected? This one will be connected. And what is S0 complement? S0 is 1. Complement is what? 0. Means, is it working as like this or not? Right? The same thing you can read around like this also. See, from the next time onwards I won't explain. So the same thing I can able to read around like this. S0, I can take the another circuit line. This is 2 by 1 mux, Z as output, and the inputs are S1 complement as well as this also S1 complement. Right? Now, for example, let me try to take one more thing. Project of 1 comma 2. Can you able to implement the multiplexer for this? Right? So what you can do, simply you can write its complement form. Its complement form is what? Summation of 0 comma 3. Summation of 0 comma 3. For this you can able to draw 4 by 1 mux for the coming class and 2 by 1 mux for the coming class. Okay, fine. For example, let me try to do one more thing. Summation of 1, 3, 6 and let us take as 7. Whatever may be it number. Whatever may be the number. Right? Now the question is, how many inputs are there, how many minterms are there here? 4 minterms. 4 minterms are there. 1, 3, 6, 7, meaning that when we are going to pass 1 or 3 or 6 or 7, I need to get the output 1. So can we be able to implement 8 by 1 mux? Can we be able to implement 8 by 1 mux or not? Yes, we can able to implement 8 by 1 mux. 8 by 1, right? So 0, 1, 2, 3, 4, 5, 6, 7. And how many select lines are there? S1, sorry, S2, S1, S0 and its respective output. Right? To make the output as 1, what are the select lines you need to select? 1 need to be taken out, 3 need to be taken out, 6 need to be taken out and 7 need to be taken out. Its input I have to connect it as 0. I have to connect it as 0. And what about all these inputs? I have to make it as 0. Now you can observe, whatever the input that you are trying to give, it is going to be acted as same as basic AND OR gate representation of 1, 3, 6, 7. Am I right? Right? Now can we able to implement with the help of 4 by 1 multiplexer? The inputs are here 4 and the inputs here are 2. I am going to take it as S2, S1. You can take S1, S0 also or S2, S0 also. That depends on your interest. Okay, fine. So what I can do now? I will try to take S2, S1, S0, 3 zeros, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Right? So at what case you are going to get the output 1? You are going to get 1, 3, 6, 7, right? 1, 3, 6 and 7 and all the remaining cases you are getting the input as 0. Right? Now with the help of this analyzation, can I say that if I am going to have S2, S1, both values as 0, I am getting what value? S0, which is same as like S0. If I am going to have 0, 1, 0, 1, what output I am expecting? S0. Similarly, 1, 0, 1, 0, what output I am expecting? It is independent of S0, 0. If I am going to have 1, 1 as input, 0, 1 you are getting, sorry, 1, 1 you are getting, so it is independent of again S0. So what values you can pass here? For first one you will pass as S0, second one also will pass as S0, third one you will pass it as 0, fourth one you will pass it as 1, then you are going to get its respective output J. Right? If you want, you can check any kind of input. For example, let me try to take one input as 101 or else let me try to take it with 110 because I need to get its output 1, right? 110. If I am going to give 110, S2, S1 is 11, S0 is 0, 0, 0, 0. Right? When we are going to call 1, 1, 1, 1, which select line is going to be selected? This one, fourth one, right? Because these names are what? 0, 0, 0, 1, 1, 0, 1, 1. 1, 1 is selected this one, so you are going to get output as 1. Is it okay? Yes. Right. So like this you can able to construct, you can able to use multiplexers somehow. Right? So in the coming class, we'll see again a few more examples. Like now, the same circuit can you able to construct with the help of 2 by 1? Yes or no? Yes, right. As we are going to construct with 8 by 1, I can able to construct with 4 by 1, I can able to construct with 2 by 1, right? Means if you are able to observe, the 8 by 1, 1, 2, 3, 4, 5, 6, 7 and 8, right? So means this is 8 by 1 actually, 8 by 1. Now can I get 2 by 1 mux? This is 1 2 by 1 mux, this is one more 2 by 1 mux, this is one more 2 by 1 mux, right? So each and everything is going to produce 1 1 as output, right? Again these two are going to be combined, again these two are going to be combined, again these going to be produced as one output, again combined, then you are going to get one output, right? Means 8 by 1 mux I can able to realize it with help of 2 by 1 mux also. Means I can able to, like, once you construct any kind of circuit with one kind of multiplexer, you can able to get it with any kind of multiplexer. So in the next class we'll see how to construct like that.